Now, how many times has this happened to you? You're watching an instructional video online. Perhaps it's how to fold some origami, but it's a critical fold that you just can't quite see because of the way it was filmed. Or perhaps you're watching an appliance repair video, and there's a critical screw you're supposed to turn, but you can't quite see which one it is.
Now, if you ever find yourself needing to disarm the Illudium Q-36 explosive space modulator in the final 10 seconds before detonation, it's vitally important that you turn the intensifier screw 18 degrees to the left before snipping the second red wire. Failure to do this could result in instant cataclysm. And so, as always, I caution you when building your doomsday devices.
Now, in the real world, it'd be a simple matter to just move your head to the side to get a unique point of view. But with traditional video, the viewpoint becomes locked as soon as that scene is filmed, and you cannot change it afterwards. So this is the promise of immersive media or immersive video. Now, that term of immersive media is one that is used across the industry to mean different things. In the context of this talk, it very specifically refers to a video experience where you can move your head and get a shift that matches. When you move your head to the side, the viewpoint of the scene will change to match that. It becomes much more like looking out of a window instead of just looking at a video more like a poster on a wall. This extra level of immersion and these depth cues is really important to our understanding of certain scenes. Scenes where an understanding of the geometry or spatial relationship of different objects in it really improve their effectiveness when we have these extra depth cues. A scene where you are trying to learn how to knit, or how to do appliance repair, or small engine repair, or learning to fold origami. All these are examples of scenes where your brain is always using these depth cues to get a better understanding of what's going on. And so if we can replicate this immersive experience, it becomes much easier to learn these types of scenes. And the experience that you're watching goes into your brain much easier because we've replicated those real-world depth cues. Now, you may not think that these small shifts in perspective have a big impact, but they actually do. Our brain is always monitoring these subtle depth cues, and we are never really holding still. Our head is always moving a little bit on at least the millimeter scale. Even when we think we're holding still, we're really not. And these subtle depth cues, these motion parallax cues, help our brain understand the world around us. So, how can we achieve this immersive media experience? Well, the typical technique is to use a lot of cameras. And ideally, we'd like to have an infinite number of cameras. That way, wherever someone's head was, we would have a camera there and we could just show the viewpoint from that camera. Now, the problem with using an infinite number of cameras is, well, there's a couple of problems. One, the cameras intersect and overlap with each other. You can't put the cameras that close together. So there's also the problem that an infinite number of cameras is very expensive. And so the problem we want to solve is that we're going to have a fixed number of cameras. But a person's head position may be between some of those cameras, so we need to interpolate an intermediate position using the adjacent camera views as references. This is actually a pretty established field of study going back decades. One popular approach is to use depth as an information. You calculate the depth of the scene, and you can use that along with the intrinsics and extrinsic parameters of the camera model to interpolate a particular camera's view into a standard world space that all the cameras can interoperate on, and you can try and get a sense of the 3D scene from reconstructing all these views from the camera spaces into a global world space. And that approach works well for certain situations. It does tend to be quite computationally intensive. And for certain scenes, depth is ambiguous. If you have smoke or fire or translucent objects, a single pixel may see objects of several different depths. Now, one relatively new technique for doing viewpoint interpolation is a technique called multi-plane images, or MPI for short.
So the basic concept behind MPI is to take a fixed set of camera images and then run them through a previously trained machine learning model to generate a stack of MPI planes. And each of these planes is going to have a color texture and going to have an alpha texture. So you have an RGB alpha. And this slide here, we're showing them side by side. I'm only showing 3 of the planes so you can see a little more detail. But in practice, there will be any number of these. 32 is what we've been using for our work here. And so if you take these planes and stack them on top of each other, like layers of glass stacked on top of each other, and then put a virtual camera at the top of them and kind of look down, you get this experience where you can then do viewpoint interpolation by moving the camera from side to side to get this little parallax effect. And so this looks pretty good. And it's got some clear advantages. And one of those advantages is that rendering a single stack of MPI planes is really trivial for a GPU, because GPUs for decades have been optimized to draw triangles. And this is basically 32 triangle pairs or 32 quads with an RGB alpha texture onto them. So rendering an MPI stack is very, very easy for a GPU. Now, there is a big problem with MPI, and it's a problem of bandwidth. If we say we're using a stack of 32 planes, and we say we're going to run this at a 1920 by 1080 resolution, at a frame rate of 30 frames per second, that comes out to 8 gigabytes a second. Now that will quickly fill up a hard drive and obviously will exceed your network bandwidth for most people. So we need to apply some compression here. As you can see, this is the full stack of 32 RGB alpha planes, and there's quite a lot of information there. So what can we do? Before we go into the details of how we want to tackle compression, it's worth mentioning that in this framework, we're relying on the Local Light Field Fusion software framework. This is a pre-existing open source software stack that has been published previously, which lets you download your images and generate MPI stacks out of that. And the way this particular MPI generation stack works is kind of on a camera by camera basis, by which I mean if you feed in 16 cameras, the output of this framework will be 16 MPI stacks, each of those centered at these 16 input camera positions. And then to generate an intermediate viewpoint, the default LLFF renderer interpolates the result from the nearest 5 MPI stacks. So basically, it renders the scene 5 times and then blends the results together. Now, we did have to make a few minor modifications to this framework to allow us to run some video sequences and to get it down to being able to work with only 5 cameras. As we turn our minds to the problem of MPI compression so we can apply it for video sequences, we focused our efforts on using traditional video codecs. And we did this because there's literally billions of PCs and consumer electronic devices across the planet. They already have hardware video decoders. So let's try and use those in this space rather than making a brand new codec from scratch, which wouldn't exist out in the real world. So the first problem we run into is that video codecs are typically 3-channel YUV in the 420 format. If you're not familiar with YUV, it's very standard in the video industry. Basically, Y is a monochromatic signal at full resolution, and the U and V are color channel information. And this is used because, well, it goes all the way back to broadcast television when we started doing black and white transition in a backwards compatible fashion from black and white into color. But the main point here is that if you look at a YUV 420 signal versus an RGB signal, we could do a pretty simple color space conversion between the two, but the color component gets downsampled from 1 color sample per pixel to 1 color sample per every 4 pixels. So this immediately gives us some compression. So that is a good thing. So mapping MPIs from RGB alpha into the YUV space that video codecs use is something we're going to have to figure out. And basically we can take the RGB textures and convert them to YUV 420. Now, like I said, this is going to result in some color decimation, but humans are usually not quite as good as seeing color loss compared to intensity loss, which is why we use YUV 420 so much in the video field. But in the context of applying this to MPI stacks, we need to make sure that that holds true and we don't see a big performance loss in quality. So to do some quantification of this and some other concepts we're going to describe, we chose a piece of test content called Technicolor Painter. And Technicolor Painter is a video sequence. It's a 4x4 grid of cameras, which we've labeled V0 through V15, which you can see in the lower right corner of this diagram. And we also picked some intermediate viewpoints we call C0, C1, C2, and C3. And you can see how those lie at the midpoints between some of the center camera clusters. So again, the V labels are actual camera positions, and then the C positions are positions in between the cameras for which there is no camera data. And we'll do that. We'll use those points for some of our viewpoint interpolation measurements. And so that is our test content. So what we did in order to quantify the visual impact of using YUV420 coding, we first generated the 16 MPI stacks using the camera positions in the original cameras. So that gave us MPI stacks in 32 RGB alpha format at V0 through V15. And then we took these stacks. And we took the RGB components and converted those to YUV420 for our color textures. And then we used these resulting stacks to render at the intercamera position C0 through C3 to see how the viewpoint interpolation held up when we converted to YUV420 and converted this against the original 32 RGB based textures. And so here are the results for the intermediate camera positions of C0, 1, 2, and 3. You can see they're all pretty similar here. And these PSNR values are pretty high. So we can see there's not a real big loss in quality when we convert from RGB to YUV, which is a good result. And it's worth mentioning that this is a very minor degradation in quality, but we're able to reduce the pixel rate by 1.8x, and that's because we're doing a chroma subsampling, a color subsampling, as we go from RGB to YUV420. So now what we did is we wanted to compare the results against the original camera images. And so what we did is we rendered the scene at viewpoint 5 and viewpoint 9, which, if you look at the lower right here, are some of our center camera positions. And we compared that we used the YUV420, compare that back to the RGB original texture version of the MPI stacks. And we did this in two ways. We did this first when we call all stacks. In here, we feed all stacks into the MPI renderer. And so even though we're rendering at view 5, we're actually giving the MPI stack located at view 5 into the renderer. And it is heavily relying on that to render the intermediate scene. And then we did the similar thing where we withheld the stack. So we wanted to render at view 5, but we held the view 5 MPI stack from the LLFF MPI renderer, just to get a sense of how the viewpoint interpolation works when you compare it against the real-world camera scene. And so you can see that there is a drop in quality here, especially if you compare us withholding the local stack, but this is what you would expect, because we basically have removed information about the scene from the renderer, and it has to do a bigger guess on what the viewpoint interpolation actually is. But the good results is that these are all still reasonable viewpoint interpolation quality levels, even though we've moved from RGB to YUV for the color texture. Now that we've solved the problem of moving from RGB into YUV space, we can run this stuff into a standard video compressor. So you could think, well, we've got 32 different layers. Can we just do a brute force video encoding and have 32 bit streams? And we'll encode 32 streams of YUV for the color and 32 streams of monochromatic video for the alpha channel. Now, you can do this, but playback becomes a bit of a problem. Now, we do have Intel GPUs that can decode this many streams, but it's a lot of pixel fill rate and really saturates your memory pretty quickly. Plus, there's also the problem of how to stream all this information to your house. So if before you had one stream coming in at 10 megabits per second and we need to do 32 of those, that suddenly becomes 320 megabits per second. So we need to find some way to make this a little bit smaller. So what can we do? Let's take a look here at these planes again. Again, this is just a subset of 3 from a stack of 32. And the LLFF framework generates a unique RGB texture for every level of the 32 planes. And as we stare at these, and it's a little blurry in this version, but you can see that there's a lot of coherency here. And so we eventually got to a point where we said, what if we just use a single color texture for all 32 planes? And we experimented with some different techniques, and we found what worked really well was basically just use the original camera picture as the color texture for all 32 planes. So we call this format the 1YUV 32A, indicating we have one YUV color texture and 32 alpha channels. And basically, we just disregard the RGB data coming out of the MPI generator from LLFF. And instead, we use this original camera image. And we keep using the original 32 alpha planes coming out of the MPI generator. So we again rendered some intermediate viewpoints at the C0 through C3 points using these YUV 32 alpha stacks. And as you can see, if we compare against using the original 32 RGB alpha as our reference truth here, that the 1YUV32A approach shows an average reduction of about 0.5 decibels compared to doing 32 YUV. And this is an important result because we got a very minor degradation in quality, even though we reduced the color texture rate by a factor of 32x. So this is significant. Now, in this table, we're comparing against intermediate viewpoint rendering done by the MPI framework. But what we really care about is what the scene looked like in the real world. And that's why we are using this view 5 and view 9 positions shown here. And so what we've done here is like we were doing a little earlier, is we're rendering the scene at positions for which we have real world reference images because we have a camera there. And we removed that camera stack, this MPI stack corresponding to that camera position, we removed that from the renderer. So when we render at view 5, the view 5 stack is not there. And when we render at view 9, the view 9 stack is not given to the renderer. And so we're doing this so we can do viewpoint interpolation and compare it against the actual real world scene. And so when we do this, and we look at the results for the 32 YUV textures versus just one YUV texture, we actually see an improvement in quality. The one YUV approach, using the camera as ground truth, will actually give a better result than if we had used the 32 textures derived from the textures coming out of the MPI generator. So this is a great result. We've done a 32x reduction in the color texture size, and we've even slightly improved the quality. So now that we've been able to collapse all the textures, the color textures, down to a single plane, the question is, now can we collapse the alpha planes, of which there are still 32, into a single layer, or at least smaller layers? And yes, we can do this. We experimented with several different techniques, but basically the sparse nature allowed us to code these 32 alpha planes as a single alpha map. And it looks something like this. This picture here is a representation of all 32 alpha layers collapsed together. And so here on the left-hand side, we see one of the original 32 alpha planes. And when we go to the right-hand side here, this is one of the planes that we have reconstructed from that single alpha map. And so there are definitely differences between the two, but they are at a high level pretty similar to each other. So let's go ahead and quantify the results there. Again, we're going to render at the C0 through C3 points, and you can definitely see a bigger loss in quality here. Again, we're using the original render 32 RGB alpha stacks as a reference for our PSNR calculations. And the quality drop here for using a single alpha map in the 1 YUVA format is about 3 dB, which is more significant than we saw when we were just using the single color texture with 32 alpha channels. But this method, again, uses 32x fewer samples to store alpha information. So this is a place where we are getting a loss in quality, but also getting a very substantial reduction in data size. And so if we do our similar experiments where we render the scene at the intermediate camera or the actual camera positions, our quality degradation is actually pretty minor if we look at the 1YUVA format versus the 1YUVA 32 format. If we look at places for which we have real-world imagery, we see a very minor loss in quality, even though, again, we had a 32x reduction in the alpha data rate. To summarize these past few thoughts, we started with 32 RGB alpha planes, but have been able to compress that down or collapse that down into a single YUV alpha plane, resulting in a 51x reduction in pixel rate. And now, rather than having to run 32 pairs of textures through a video compressor, now we just have one texture pair we need to run through it. So already we've made big gains, and we haven't even applied video compression yet. So what we're going to do now is apply video compression to these texture pairs we have just described. And so what we did is we used the HEVC codec to compress these MPI stacks at all 16 camera positions in the three flavors we've talked about: 32 YUVA, the 1Y 32 alpha, and the 1YUVA. And we coded these at 8 different QP pairs, and we have a different QP for color versus alpha. If you're not familiar with video compression, the QP is basically correlating to a quality level. And so what we are doing here is compressing our bit streams, compressing our video sequences at different quality levels to see what level of bit rate we achieve at those different quality levels. And so we have different quality levels we've set for both the color and the alpha textures. And it's worth noting that we didn't really require any private extensions to the codec, and we're able to use off-the-shelf analysis tools because we weren't doing anything that required codec changes. So let's look at some curves here. All right, so we've got a lot going on here. And if you're not familiar with rate distortion curves, let's walk through this. We're showing 3 different results here. The red line with the circles on it is showing the results for the 32 YUV alpha format. The green line with the square dots is showing the results for using 1 YUV 32 alpha version of the MPI stacks. And then the blue is showing the results for doing a single 1 YUV alpha version of the MPI stacks. So that's what our data points are here. And what we're showing on the right-hand axis is the megabits per second of the bit rate. And we're showing the PSNR values as our vertical axis. And what we've also drawn on here are some horizontal dotted lines. This lowest dotted line is showing you the PSNR value we're able to achieve before we applied video compression. So this is the PSNR value that you can achieve prior to compression, and it kind of serves as a theoretical maximum quality level for that format of content. And the second green dotted line with the shorter dots on it, that is showing the uncompressed PSNR for 1 YUV 32 alpha format, and then the top very small dashed line in red is showing the PSNR value, the quality level, when we did not compress the 32 YUV alpha. So again, each of these dotted lines kind of serves as a maximum quality bar you would expect if you ran the content through a video compression sequence. And so each of the points on these curves is corresponding to one of the QP pairs we showed in the previous foil. So if we look first at these red curves, this is showing us a couple of things. It is showing us that in order to achieve maximum quality, using the 32 YUVA format, it takes a very, very high bit rate. It's not shown here on the graph, but it tops out at over 300 megabits a second. And also, what this graph is kind of showing us that for any bit rate below about 80 megabits a second, that the 1 YUVA format has a clear quality advantage over both the 32 YUVA and the 1 YUV 32 alpha formats. And given that most streaming applications use a much lower bandwidth than 80 megabits per second, it's this left-hand side of the graph that's really telling us what is interesting. So let me walk this through in a different way. If I want to achieve a PSNR quality value of, say, 40 I can look at where the dotted line intersects here, and I see that I can achieve a PSNR value of 40. And I look down and I can see that's running about 5 to 6 megabits a second. I can achieve a PSNR of 40. If I want to achieve that same quality level using this 1YUV32 alpha format in green, I have to spend more like 25 megabits a second. And then if I want to use 32 YUV alpha format, which is the biggest one, I have to spend more like 42, 45 megabits per second. So this is saying that for real-world data rates, the 1YUVA format is the way to go. Now, we also calculate the BD rate for the Y, U, and V channels here for the 1YUV32 alpha and the 1YUVA format. And basically this shows us that the 1YUV32A format results in a 25%, approximately 25% lower bit rate for the same quality than than the 32 YUV. And then if we go to the 1YUVA format, we see a whopping 88% lower bit rate required. So again, this is telling us that there are substantial quality gains and bitrate gains to be had by using this 1YUVA format we have come up with for coding 32 RGB alpha. And so we do the same sequence of experiments here in graphs, now looking at the camera positions V5 and V9. And we see a similar story here. And so again, any bitrate below 80 megabits per second, 1YUV alpha holds a clear quality advantage. And we see that reflected here in the BD rate for these same viewpoints, View 5 and View 9, with the local cameras withheld. So to summarize our investigation here into compressing MPI stacks, we've shown that we can reduce the pixel rate of the original stacks by a factor of over 50 and compress them using existing codecs while reducing the compressed bit rate by about 90% while retaining a reasonable level of quality. Now these reductions in pixel rate and bit rate make the storage and transition of MPI content much more feasible to support on real-world existing systems today. And so with that, we'd like to show a demo of this working on a real-world existing system. What we did was wrote an application which takes in a compressed 1YUVA format bitstream and does a hardware decode of it on the Intel GPU, and then expands that out into the 32 alpha planes. And we use the camera texture and do a real-time rendering of the content. And we're using a web camera to keep a track of the viewer's head position and re-rendering the scene based on where the viewer is for every single frame.
So here we are in the lab, and we've got Sumit in front of a webcam, and as he moves from side to side, you can see a change in parallax showing up on the screen for this short test clip we're looping backwards and forwards. The clip is playing in slow motion, so you can get a sense of the fire effect and how we're changing the parallax of the scene. What we can actually do to kind of prove the viewpoint interpolation is going on is pause the scene when the fire is out, extending here in just a second. And there you go. You can see that we've paused time, but we can still move from side to side and get some motion parallax. And then we can resume playback whenever we want. So it's a little hard to see what this experience is really like unless you're in front of the screen. We're going to try and simulate that by putting a GoPro camera on Sumit's head here and show you the experience from that point of view. So here we are with a camera strapped to Sumit's head, and as he shifts from side to side, again, you can see the parallax changing to match that motion. And again, we can pause time if we want to, move from side to side to get a sense of the parallax. And you can see the change in the reflections in the windows and the movement of the background and like the light reflecting off of the countertop. So again, it's really hard to experience it in its entirety unless you're right in front of the scene itself, but hopefully this gives some sense of it.
Now, there's still plenty more work to be done. For starters, we're expanding our range of test content. We're also looking at cross-camera compression. And we also have some ideas for improving the alpha map quality. We're also extremely interested in collaborating with content creators. We believe that this technology can be the basis for a more immersive visual experience. So if you think that your channel of content can benefit from this type of technology, by all means, reach out to us and we'll see if there's a way that we can collaborate. Finally, although it has been me doing all the talking today, the work you have seen here is the result of a collaboration across a team of very talented individuals. And I must thank them for all their hard work to make the technology we have shown here today a reality, where we have brought volumetric video through innovative compression techniques to mainstream GPUs. So we hope you have enjoyed this talk, and we'll see you in the future.